Dear colleagues, good afternoon. I apologize for the short delay, but the previous session was fascinating. And welcome at this session on artificial intelligence, robotics, and remote handling in the nuclear field. Before starting, let me share my deep thoughts for the hundreds of victims due to the massive floods that have affected a large part of Europe these last 2 days. And I present my sincere condolences to the family of the victims. And I'm also convinced that the European Union will support the reconstruction of the damaged built environment. Dear colleagues, this week, to fight against climate change, the European Union has presented 12 legislative proposals in the frame of the European Green Deal and the carbon neutral objective by 2050. The so-called Fit for 55 package will need structural transformations to reduce greenhouse gas emissions from all economic sectors, including energy and industry. Innovation will be needed in all technologies in order to achieve these targets. And artificial intelligence and robotics in the nuclear field can offer many advantages and opportunities in the sector. For speaking about this issue, we have 1 hour with two distinguished speakers, Carlo Damiani and Jean-Reynald Massé. Let me just introduce Carlo Damiani first. Carlo is a nuclear engineer. He worked at Enea Brasimone Research, serving as experimental engineer from small-scale lab test up to the ITER RH project, diverter remote maintenance. In 2000, he worked for the European Fusion Development Agreement, the EFDA Close Support Unit in Culham in the UK. And he worked as project manager at JET. From 2004 to 2006, he was seconded to the Institute for Plasma Physics in Germany, where he was the head of system integration department. Then he worked in EFDA Garching, dealing with the ITER diverter remote handling. Carlo Damiani is now the program manager of the remote handling group, machine system division in the ITER department. I'm very glad, Carlo, that you are there, and we are very happy to listen to you. Thank you, Carlo.
Thank you, Mr. Rossetti. Thank you, everybody. And yes, I'm going to give you some flavor of what we do in the fusion program in the ITER. That is the big chunk of the fusion program in an area that is maybe not, let's say, 100% artificial intelligence, but nonetheless, we are working on introducing advanced robotic features into the systems that are going to maintain the ITER nuclear reactor. So if you could go to the next slide, please. Okay, so this is the outline of my presentation. I tell you what is ITER and what is ITER remote maintenance, a brief overview of the remote handling system, and some hints about the robotic features we are developing. Next slide, please. Okay, so you see here an artistic view of the ITER tokamak with a plasma inside. Actually, it's a fake plasma, it's glowing plasma. In reality, you would like in ITER to have a plasma as dark as possible, because plasma should emit only in the X-ray and gamma ray field, let's say, not in the visible range. I have also dotted in red the areas of the tokamak building that you already see here. Is quite a complex plant system, and actually let's say the tokamak itself is at the heart of the tokamak building, is exactly where the plasma is glowing in this picture. Nonetheless, you can see that all around I have dotted lines where we have to perform maintenance of the equipment that are inside, because maybe they are damaged, because some of these components have reached end of life or whatever. And these lines shows where we cannot get there with human intervention. Basically, if ITER will be a success, as we all hope, and if there will be intense nuclear pulses, the neutron activation, because of the fusion reactor, will make inaccessible all this area, and in particular the core of the machine, for 1 century, if you like. So because we cannot wait 1 century to make a repair, we need remote maintenance. This is basically the key message that I want to give you. And remote maintenance here is extremely complex. as the topology of the ITER reactor is complex as well, and the amount of components that to be maintained, the geometry, the size, the multi-ton weight, etc., is such that all this remote handling tasks must be performed in a way that is novel, is unprecedented in the technology, let's say, and in science. Next slide, please. So here you can see the ITER site. It's a relatively recent picture, and you see there is the gray building, the tall gray building in the middle is the assembly hall plus the tokamak building that is a little bit far away. So the tokamak building that you have seen in the previous picture is the second half of this long, tall gray building. So this gives you an idea of the scale of the ITER project. It's really gigantic. Let's go to the next slide to speak a little bit why ITER needs remote handling. And this is a very common slide that we in the fusion world show, that is showing the fusion reactor, the fusion reactions between deuterium and tritium producing neutron and energy. And of course, energetic alpha particles that will give back the energy to the plasma to keep the plasma, to contribute to keep the plasma hot. And the neutrons instead leave, let's say, the plasma chamber because they are neutral, so they are not trapped by the magnetic field, the powerful magnetic field that we generate in ITER, and therefore they will hit all the surrounding components, and the heat will be taken away by water, and this is the principle of making fusion an energy source. But this neutron hitting structural material means these materials will become activated, will become gamma emitters, and this means that people cannot go around and cannot go inside to make maintenance. If you click again, please. Okay, this is just showing a little bit certain parameters that we have to follow in order to have this a suitable nuclear reactor here. So maybe somebody that is not in the field would ask himself or herself, why do we have such a strange donut shape, and why all the tokamaks are like this? It's just a combination of constraints and conflicting requirements that at the end makes such that this is the best shape today with all our knowledge of plasma physics and technologies. This is the best shape that would give us the road to nuclear fusion and the road to exploitation in commercial terms of nuclear fusion. And the ITER is like this, demo will be like this, a little bit bigger, and also in the past, JET, that is the predecessor of ITER, was like this, but was not nuclearized at the level of ITER, of course, because ITER is really a first of a kind full power fusion reactor. Next slide, please. Okay, so this is just to give you an idea of how we scale up from JET, that is the existing tokamak, to ITER. And here in all these texts, I wanted just to show that all the neutrons, as I said, are absorbed by the blanket and divertor, that so will be also damaged by all these neutrons and by the interaction with the plasma, and they would require maintenance, replacement. And because of this, we have calculated that to go to the level of neutron activation in ITER, like in JET, we have to wait more or less 100 years. That is 20 times the half-lives of cobalt-60. That is one of the components of the ingredients of our structural steels. And this means that this is a really harsh environment, and no human being can go there for a second, I would say. And this means also that all the systems that we have to introduce there must be rad hard or rad tolerant to 1 mega grayscale. So this is also a technological lead. And of course, the size of the components is big. Everything is gigantic in ITER, and therefore all this means that there is a lot of novelty and a lot of challenges in what we're going to do. Next slide, please. Okay, this just to show that the red zone is the level of total dose rate for nuclear fusion reactor like ITER, that is just a little bit below in-pile fission reactor, that is the top right line, dark line. But in-pile fission reactor maintenance is much easier, much simpler. You have just to extract up and down, to take up and down the fuel assemblies, while in ITER maintenance is a much more complex business. Next slide, please. Okay, just to give you an overview of the remote handling system we are developing for ITER. I believe you all know that ITER is a joint effort of Europe and China, Russia, Japan, South Korea, India, and US. So it's a worldwide experiment, and Europe is has got the lion's share, if you like, because the ITER is in Cadarache, and Europe is the major partner of this enterprise. We, as Europe, we also are in charge of some of the remote handling system of ITER, and if you click, I will show you which are we have 4 major remote handling systems. One actually is a diagnostic system, investigative system, but these are all, we have a large fraction of the ITER remote maintenance in terms of design and manufacturing. Next click, please. Okay, so here you can see the 4 main systems that we are developing for ITER. On the top left, you see divertor remote handling. The divertor cassettes are this strange V-shaped or W-shaped components. These guys are as big as a Fiat 500, if you like. Just half of the width, but the rest of the dimensions is the same. And you see these gray bits that are acting into the area are our divertor remote handling system that are in this case handling one of these 54 divertor cassettes. Each cassette is 10 tons of weight, so it's a huge component, multimeter dimension that must be installed and removed with millimetric accuracy. It's really a feat. All this, and all these components will travel into the tokamak building with by means of casks that are the blue bits on the top right picture. There are 3 kind of casks. On the top level is the upper port, equatorial level is the equatorial cask, and the lower level there are the divertor casks. And each one of these blue bits is as big as a bus, so we are speaking about gigantic scale. On the bottom left, you see the neutral beam cell that is as big as a hot cell in nuclear fission, I would say, and is full of components, full of devices. In this picture, you see only our remote handling system that includes a monorail system attached to the roof. That is a 40-ton nuclear-grade crane that is able to operate in this neutral beam cell. And last but not least, on the bottom right, you see the investigative system, where basically we perform inspection, for example, overnight or during the weekend in between plasma pulses. And with a laser-based system, just to tell you that in between pulses, the ITER inside is totally dark. It's as dark as a cave in the heart of a mountain. So every system that goes there to make maintenance or inspection must be self-illuminating. And this is the case also for investigative system. That is able to launch monochromatic laser spots onto to recreate pixel by pixel the full image of the in-vessel, to understand if the in-vessel components are damaged by the plasma or if they're okay, still can operate for the next plasma campaign. Next slide, please. Here, it's just to give you an idea. This is on the top left, you see the neutral beam cell that I was mentioned to you before, and now is full of stuff, full of injectors. Each one of these injectors is to inject neutrals, energetic neutrals into the plasma, to heat the plasma to the 150 million degrees that is needed to have the favorable reaction rate between the deuterium and tritium. So one of these heating systems is shown here on the right side of the slide, is a neutral beam injector that injects 16 megawatts of power into the plasma. And to give you an idea of the scale, you see the bottom left picture. There is one mock-up, full-scale mock-up of the rear side of the injector, and you see the 2 men there, and this gives you an idea of the scale of what we are doing in terms of remote maintenance. It's really gigantic, and in the reality, no man will access this rear door of our injector. There will be robotic systems that will make use of extensive usage of technologies to make it. Next slide, please. And here you see the remote handling control system diffused in all the ITER plant as that is a diffused system, and we have the high level where we put a lot of robotic features that I'm going to speak about now. I'm conscious that time is running, so I try to give just next slide, please, to give an overview on some key features in terms of robotics, advanced robotics for our remote handling system. Here, just to show you the breakdown of our control system between the bottom part that are the devices, the field equipment, like the diverter remote handling system operating inside the tokamak. After we have the cabinets, low-level control system, and we have the pink boxes is the high-level control system that is located in the remote handling control room. And here you see some of the remote handling systems that we are going to operate remotely. Next slide, please. Here you see the architecture of our control system, and you see that there is, as I said, the high-level control system in the remote handling control room, and this also there is a remote handling network infrastructure, and via a remote handling supervisor that is on the right, we speak to the rest of the ITER plant because, of course, ITER is a nuclear system. But during maintenance, we have to operate, and the nuclear system must stay in a safe, idle state while we operate and we make maintenance. And so there is a large amount of communication between the different, the remote handling control room and the ITER central control room, the ITER central system. Next slide, please. And here you see the little bit the overall architecture. You have the central INC system on the top. You have in the middle the remote handling supervisory control system, and in the bottom part all our systems, individual systems like the diverter remote handling, cascade plug remote handling, etc., etc. And if you click again, I believe you see, yes, you see the two halves. As Fusion for Energy, as Europe, we are responsible for the bottom part, if you like, of the remote handling control system. Next slide, please. So let's have an overview of the robotic features we have developed. Here you see the three levels of our control system that I was mentioning to you before. And if you click, you see that we have the basic distinction between the high-level control system that is for the interfaces for the operator, for the plan and the execution of the remote handling operation, and the low-level control system that really performs the activities. The operator dictates, but what is really executed is responsibility of the low-level control system and of the field equipment. Of course, the operator has the ability to intervene from the top and with a series of remote handling control features that I'm going to illustrate. Next slide, please. Okay, this is a view on the high-level control system where the operator operates actually with the various features that are condensed here. You can see that there is in the pink box you have the operator management system on the top left. That is where the operator decides which kind of task, elementary task to perform. You have also haptic devices like a master arm or another device that is like a joystick a little bit on the bottom. You have also virtual reality embedded into the high-level control system to provide a virtual 3D environment and also to assist the operator with collision avoidance. And we have also the viewing system that is part of and we have a remote diagnostic and a series of other features. And let's go to the next slide, please, that we will go a little bit more in detail on this. Okay, this is just a view of how one portion of the ITER remote handling control room could look like. Of course, the ITER remote handling control room would be much, much bigger than this because we have many, many subsystems that I've shown to you some of them. But each one of the these systems will be operated from a workstation, a remote handling workstation that is a little bit like this, with all these features, viewing capabilities, virtual reality capabilities, and other control and command capabilities, including remote diagnostics. And here you see the various development that we are performing. We are performing the development of control and command, human-machine interface that are specifically tailored and ergonomic for the operator. And we are also working on remote handling input devices to operate, for example, a manipulator arm that is a force feedback manipulator in order to have the right dexterity to perform, I don't know, pipe cutting and welding in order to detach or attach a divertor cassette into the vacuum vessel during at the start or at the end of the maintenance period. And we have also remote diagnostic features that are on the right. That is basically because each one of our systems is extremely complex. In order to understand if the system is healthy, is not going to fail during an vessel intervention, that would be a disaster, because there is no way we can go there and repair the remote handling device. So the remote handling device must be reliable and self-recoverable. So having specialized, developed diagnostic features is something that we are doing right at the moment in order to enable and to enhance the reliability of our operation. Next slide, please. Here there is the virtual reality. We are using VR for robots, and is a software, a commercial software that is powerful enough, performing enough in order to provide the operator with all the virtual reality additional information that is needed in order to reconstruct the full environment of operation. Because as I said to you, when we enter into the vessel, we have only a few cameras available, a few lights available. So the vision of the operator with the viewing system from the control room is limited. Virtual reality is going to complement all this, but of course must be a virtual reality that is reproducing the real movement of the real machine. So there is a master-slave configuration, and also there must be collision avoidance features in order to avoid that the operator is making some big mistake, is going to hit with the tool and is going to lose the tool or whatever, is going to create an incident inside the vacuum vessel, for example. And also the virtual reality is also useful to plan, to simulate tasks before executing the real task. And here we have a viewing system that is far from being trivial, because we need very small cameras due to space restriction, but these cameras must be 1 mega gray. That means must be really rad-hard cameras, and we are developing innovative cameras that will collect the images, and all these images will be sent to the operator. For example, if we have to perform a welding, we need miniaturized camera that are really able to look at the weld seam, and this is essential in order to perform a welding that is, for example, for a water-cooled pipe. And if welding is not successful, you have a water leakage into the vessel. It will be a disaster. So to have reliability and feasibility even, we need an effective system, and we're developing all this. And also, we are using retroreflective markers, as you can see here, that we are developing also this part of technology in order to assist the operator in centering and in engaging the tool with the manipulator arm in the right location. So this is in order to increase dramatically the dexterity of the operation that we're going to perform. Next slide, please. And here are just a few snapshots that I put here, not in a particular order, just to give you a flavor of all the real laboratory activities that we are performing in many different fields in all this for our remote handling systems. We have seen a lot of diagrams so far, also a lot of virtual reality. Now you see some real hardware, some real laboratory tests. So it's a complex program that we are developing right at the moment, and it is keeping us busy and will keep us busy for the years to come. And in this respect, ITER will, in terms of advanced robotics, and if you like, also some hints of or some flavor of artificial intelligence in the nuclear field, will be first of a kind. Will be first of a kind not only for nuclear fusion, but also for this innovative nuclear technologies in the field of remote maintenance. I believe this is the last slide. Yes, this is demo. Demo is just a big ITER, if you like, and many of the issues that we are facing in ITER will be faced also in demo. So the technologies that we are going to use are going to be reusable, recyclable also for demo. There is a difference that in demo, the 1 megagray scale is not enough. We need 5-10 megagray scale for our devices, because the demo will be much more powerful than ITER and therefore will be much more radioactive. Okay, I believe that this should be really the last slide. And I believe there is, I don't know if there is time for question now or at the end of the session.
Thank you very much, Carlo, about you're also passionate about the sector, which I feel it's extremely useful because we need passion in order to advance. Let's take the question on Slido, please, to all the participants. There are 75 participants. Do not hesitate to type your question on Slido. This works quite well, and then we can take the different questions. Dear colleagues, yes, all the questions on Slido. Let me introduce briefly Jean-Reynald Massé en français, Jean-Reynald Mace in English. He's an expert fellow at the Innovation Department of Orano. Jean-Reynald has been for more than 20 years, he has developed onboard electronics and communication systems for dual-use industrial applications. He started his career at Dassault Electronique as technical expert in integrated circuit design. He then joined for 10 years a US company, world leader in programmable components. Today, as expert fellow at Orano in the nuclear field, everybody knows Orano in Europe, he's in charge of the transformation program towards Industry 4.0. In this context, he developed the group technological roadmaps for 3 major fields: the augmented operator, the smart factory, and the supply chain. Jean-Reynald also manages a project portfolio aimed at concretizing and deploying this industrial transformation on site in the earth of industrial facilities, in factories and mines, to further improve employee safety and the performance of the group activity. Thank you, Jean-Reynald, I give you the floor, and we are very happy to listen to you. Thank you.
Okay, thank you for the introduction. I will try to be as passionate as my previous colleague. And hello, everybody. I will show you what we are doing in terms of innovation at Orano in terms of robotics. It was a key subject for us, and I will show you why. So next slide. So I will just give you some few words of Orano, and after I will talk about 2 use cases. One is a UAV, a drone we have developed for indoor inspection, and another great application where we are combining a lot of smart technologies. It's a nuclear waste sorting robot for waste management. So next slide, please. So I will present Orano in a few words. So our mission is to develop nuclear as safe, sustainable, and cost-effective energy source to produce low carbon electricity. So today we are 16,000 people in the world. Our revenue is 3.7 billion. And we are half of the company in France and Europe, and we have a part of it in Asia and 50% in America. So next slide, I will just show you where we are dealing. So we are starting from the mining. We have mining in Niger, in Africa, in Kazakhstan, and in Canada, McLean. And so we are extracting the raw material, what we call yellow cake. And after the yellow cake, you need to cleaning and conversions, where we will produce UF4, what is tetrafluorouranium. And after you have to convert this uranium in hexafluoride, it's a second step where we have in Tricastin a huge plant for conversion. After you can produce the fuel for the nuclear power plant and use it as nuclear power plants. So all these things is now dealing with Framatome and using by EDF, for example, in France. And after, when you have used the fuel, you extract the fuel, and at Orano, all the yellow pictogram, it's where we are dealing. We are processing the fuel in order to reuse the material with a process we call MOX, it's mixed oxide fuel, where we can reintroduce a part of what we are saying, mainly plutonium, at facilities in Melox, and so you can reuse it. And otherwise, when it's finished, we can store at the CGO project, for example, the long-term waste. We have another activity was is developing these days, and I think it's important that people know that we are working in alpha therapy. So alpha therapy, it's a very smart technology in order when you have cancer cells, you just attack the cancer cell, not the other. So it's a very precise therapy, and we are based on the lead 212. So we are working on that, and we hope it will be very successful. So now we are focused when we are dealing today. And as you know, as you mentioned in the introduction, in Orano, we have launched a 4.0 program to transform our facilities, to enhance the performance of our operators. And so for that, robotics is a perfect tools to use. And especially for us, it's our DNA since a long time ago, because when you are recycling useful, you are in harsh environment where you have radiation. So it's compulsory to use robotics. Robotics, all the time, you see the picture, you want to have modular platform, do multi-application, and use smart technologies. The challenge is all the time the same, make or buy. Make, you are doing yourself, but it's very costly. Or buy, you can use PCs, and the intelligence is to aggregate the right technology to make useful in your own environment. So we are still doing that with partners for a long time, like the CEA in France is Commissariat à l'Énergie Atomique, since we have developed a lot of remote handling, or like I seen some picture before, so ITER, we did the same for a lot of operation. But I want to focus on two use cases where we were dealing with startup, because in Orano we are developing open innovation, and we are making posting challenge, and we are working with startup in order to accelerate and to be to take benefit of the latest technology. So the next slide is for doing remote operation. We next slide, please. We have developed a drone, what we call ORANF. So next slide, and I will give you some what are the needs. So here you have two pictures where you can see in facilities in LAG. We have a lot of chemical processing to process the used fuel, and those processing is done in what we call hot cells, where it's human cannot be in because you have radiation, and it's a lot of tank of piping. It's a very complex environment. And in order to check if everything is okay, we have different kind of equipment, what we call important equipment for protection and nuclear pressurized equipment, where we have to do regularly check and maintenance on it to see everything is okay. So as we did before, we were using pole or mobile robot with umbilicus, but this kind of platform, robotics platform, have some limitation, and so to give a full picture where we want to check, the flying platform is the best candidate for doing that. So since I would say 6-7 years, we were dealing about how to use UAV or drone to perform inspection, and so we start with COTS drones, but we discovered that they were not fit with what we want to do. Next slide, please. And so what our difficulties is when you go inside the hot cells, you have a tube of 100 millimeter, and so you have to put in your drone and flying and come back. And so we decided to use a previous platform developed by a startup called RHCS in France was working with defense and military application, where they were using a small drone and with a foldable arm. So it was perfect for us. So we decided to cooperate. And so we built our own platform with 20 sensors, with infrared and ultrasonic sensors. And in order, we have shielding the UAV to protect any problem if you touch some equipment. And so everything should be foldable. And we did some performance in terms of radiation to see if the electronics sustains the rate we had on this kind of cells. And so it was what we have done. And so you will see the result. Next slide, please. So you see the drone picture A, you see when it's compact, and after in B, you see where we can, the way we are introducing in the hot cells the drone. And after, when the drone is inside the hot cell, we open the arms, so the drone is available to fly. And you have an antenna, we have like a Wi-Fi link, and we put an antenna inside the hot cell so we can remotely pilot the drone and to have the picture what is seeing in order to pilot and to see what we would like to check. And after we are flying, and today we have roughly 15 minutes of operational time. So in order to check in the cell to what we want. When it's finished, we go down just close to the tube where we have the drone was put inside, and we have a special tools to react and to grab the drone and to push out. At this time, we check if you have no contamination, and we can reuse the drone. If we have to perform another mission, we just remove the LiPo battery and we put it, and we can perform another check if it's necessary. We already did some tests in active cells, so we demonstrate the feasibility and the performance of such approach, because again, it's a very flexible platform, and we already save days of inspection. We permit, we can go where we want to go. And today we have done a first kind of mission. It was just visual inspection. The second phase will be we can touch equipment where we can do some ultrasonic measurement in terms of corrosion, for example. And a third type of mission will be to embed dosimetry sensors and to make some dosimetry mapping. The critical point for us is each time you put sensors on the drone, it should be light, because otherwise you reduce the operational time. So it's all the time a compromise between what we can embed and what we can use in order to not reduce the operational time. So just to give you an idea, it has been used and it will be used soon, and we have a great success with this first development. I will now move to another use case. So it's a nuclear waste sorting robot, and we have developed with another startup. So next step. So in this application, we have a silo where we have 500 tons of waste. It was previously from previous nuclear reactors or nuclear facilities or units. And what we have to perform in terms of things, it was to sort the waste, because we have different kind of waste, aluminium, magnesium, and graphite. And so the idea is to sort, and what is very important for us in terms of objective, we have to respect a limit amount of hydrogen radiolysis. So we have to be sure that what kind of waste and what the percentage of waste we can put on the container at the end. So what we decide, next please, next slide. What we decide, and you have the picture here, we have to do a complete autonomous system where you have 3 modules. Module 1 is a by-picking robot, what we call Camido now. The second module, it was identification and quantification. And module 3 is to do the sorting and the drum filling. So for doing that, we have to perform different things. The first one, it was to select and to put the waste on the drop vibrating corridor. We are cleaning the waste, and after a 3D camera and laser algorithm look how to pick the waste, and after you have to, with embedded intelligence, AI, we have algorithm to recognize what is the waste, and we can sort the waste. And after you have two corridors where you put from one side the aluminum is ejected, and another side is the waste, and we quantify the waste in terms of magnesium and graphite, and you pull on the containers. So this system is a very complex one, but you know, the feature we want to achieve, it was to have 1 piece per second and to have error rate less than 0.5%. So it was a very challenging project. We started this project in 2014 to have the idea to develop this kind of system. We developed a mock-up in 2017, and we are implementing it in 2019, and still working now, because to sort the 500 ton, it will took 4 years. So this system, you can go to the next slide. And this system is a complete solution, you know, from the silo, you have all the steps, you have all the technology, and it was a real win-win development with our partner Cilean, the French company. We have developed the picking system, the computer system, and all the algorithm to perform the sorting and to do at the speed with requirement and with the error rate we want to achieve. At this moment, 100 of the waste can be sorted. So for us, it was a very efficient system to do better safeguard condition in order to sort all the waste. So it was for us a very plus. And for Cilean, they are patented different pieces of the system. They develop a recognition module with vision and artificial intelligence. So, and the idea of the system, it's a modular system. It can be applied to another sort system, because if we have another silo, another kind of waste, it could be adapted. The system is flexible and modular, so it's a real plus for us and for the company. So we are still improving the system to use it in another application. So that's all for the 2 use case. And just the slide after, the last one, please, next one. If you want to have more information what we are doing in Orano, we have on our website, we put the innovation space where we are, the technology we are focused on these days. And we have an open innovation where we are posting challenge. And so if you're interested, you can have multiple examples, because I have video, but I didn't take the risk to show you videos of what we are doing, but you will find a lot of information on what we are doing and a lot of use cases, and they are public.
Merci infiniment. Many thanks, Jean-Renald.
You're welcome.
Pardon?
I say you're welcome.
You're perfectly in time. One typical question that I would like to ask to you, Jean-Renald, and to Carlo is, if you would have to say the three issues that you would like to tackle in terms of what research are needed in artificial intelligence and robotics for fusion, Carlo, for fission, Jean-Renald. What are these 3 points? What you would say? What are the 3 main research points where we should focus on? And what has to be done, if you can, at the national level, at European level for the Euratom program, and eventually also at international level for ITER. Can you can you give us your thoughts on this?
Okay, so maybe I can continue if you're okay.
Yeah, fine.
In terms of artificial intelligence, I think we have a lot of promising situation about, I will say, machine learning approach. Because, for example, in our case, when you know the waste, we can segment, we know the waste. So with an algorithm, you can train a machine to sort. But sometimes we have complaining about the people to say, oh, it's sure that it's working. So I think in terms of artificial intelligence, we have to make some progress in terms of how to explain the things as working to avoid the black box. Because some guys say, okay, your thing is working, but how it works? So sometimes you can, because you have a way to do it. And in our case, it was simple because we put some mock-up with different elements, so you can demonstrate that running the mock-up, you can pick the right thing and you sort in perfect way. But sometimes it's not the case. You cannot have a full test bench to demonstrate that your algorithm is 100% sure. So for me, in this kind of approach, we have to improve that to make sure that we are confident to use this kind of technique. For me, it's a very important point. I don't know if my colleague is aligned with me, but I think for machine learning, we have to improve our confidence or use this kind of approach.
Thank you very much. Carlo, your thought on this?
Yeah, no, what I could tell is that, of course, we are very much project-oriented in the sense that we have a certain obligation for ITER and we have to solve the issues that are specific to ITER. And what we are doing right at the moment is exactly in this line. We, for example, we are missing in the market some radar electronics, and we are developing new electronics that is able, for example, one of the issues is how to handle all the complex amount of sensor information in an environment that is hostile, like the one in ITER is a radioactive environment. So therefore, you mean that you need multiplexers to reduce the number of cables that are running through. That is a non-trivial problem in this kind of robotic applications. And to have a 1 megagray rated multiplexer that is able, for example, to work with analogic or digital sensors and things like this, and to digitalize the signal and to send the signal around in the network is not is non-trivial, and this is where we are working, including the cameras. For example, you have tube cameras that are 1 megagray rated, but these are relatively bulky, especially if you have a very constrained environment and they are grayscale. So there are certain areas that call for a new technology, for a new technological development. And this is exactly where we are working. And I would believe that the level of integration between virtual reality, viewing information, control and command information, to mix all this into an ecosystem that is allowing the operator to work in a reliable and repeatable way, it's a challenge. And this is exactly an area where, of course, ITER is trying to solve this for the specific problem of ITER, but probably this is valid for many other applications like the one that Jean-Mace was showing before.
Yes, in terms of camera, you know, it's an issue. For example, in Orano, we have developed our own radar camera, because camera is the key. When you put camera for a long time, you need to have reliable camera. So Radar electronics is it's a concern, but after for dismantling or the application, you have two way of doing it. You can have, I would say, regular electronics, and when it's not working, it could become a waste. But it's for dismantling because you need to have low cost application. But for operation like LAG, we have the same like ITER. We are doing radar electronic, and in order to perform some regular operation, we need to have sustainable electronics. And it's as you mentioned, it's a concern.
Thank you. On Slido, I see two questions that I will raise to you. First question: what the total integrated dose that the drone can withstand? And the second, do you have electronics components able to resist 1 milligray, and for which purpose?
Okay, so it's today we performed some tests, and I don't remember the figures, but I can share with you. But in fact, we did a regular test, and with our gamma accelerator in our facilities, and I will say perform the test. We are flying the engine, and so it was okay. I think it was less than 1 megahertz, but it was okay. When we have to perform, I will say all the ag facilities is based on technology where we remove the electronic in the green zone. For example, we have pulse column and things like that. All the sensors are, for example, mechanical, but all the intelligence are on the green zone. So one of our way of doing it is to put the instrumentation electronic part on the green zone, not on the hot, on the hot cells. And we are looking for technology like fiber optical things, because, for example, we work on radar fiber optical sensors, and we have a great advantage with optical things that you have the sensors and you could communicate the results through the same medium, is the fiber optical. So you can, again, have the interrogator in the green zone. So we are performing the test with this kind of technique. And if not, we have developed our own system. For example, for robotic, we are using brushless motors. We are developing with the CA radar umbilic. When it's necessary, we are developing radar components. But we avoid as much as possible. But when it's compulsory, we are doing it, and we are performing some real tests with our accelerators, or we perform some tests in Belgium with SKN in the pool. We've used fuel to see how it tracks. For example, when we develop our camera, we develop with the CA camera, we can be regenerated by heat. So sometimes you stop the camera, you do some heating, and so you refresh the camera, you can reuse it. But, we are using all the techniques we can use in our hands to perfect and to sustain such a dose.
Thank you very much. Carlo, do you want to add something?
Look, no, indeed, I understand the issues that the colleague is putting together, and I recognize this kind of problematics that we have. Also, the drone, it would be an interesting story, the drone. The point is that in ITER, a flying drone into the vessel is something that, it's quite hard to imagine. Also, because this drone will be fired by 500 gray per hour in the middle of the vessel after an intense nuclear campaign. So it must take a lot of gammas and survive into this gamma environment.
But again, when we start the project, we have some doubt at the beginning, because you have to change the mindset of the operator, of the maintenance guy, to say, okay, you are using regular mobile with umbilic, you are using, I will say, mechanical things to investigate. And when we show to them that we can use a flying machine, it was at the beginning difficult, but due to the benefit we will get from this kind of machine, we will be allowed to have some tests. And again, we start with, I will say, hot cells, but with the lower radiation environment. And after we are going more and more difficult, and we are doing step by step because we stabilize the flying machine. Because it's indoor, we don't have GPS. So it makes time. But again, in this case, we need to do a make, not a buy. We start with existing platform, but we use a commercial drone to make some survey of our lag site. We use a regular drone in our mining in Nigeria to measure some a lot of things on the site. But for indoor, we know that the only way to succeed was to do it with the right partner. And it took us a couple of months to select the right one. But after you select the right one, I will say it's a win-win situation.
Merci, Jean-Renald. There was one question. Are the drones commercially available?
No, it's for us. It's just it's what I call the Orano toolbox. You know, excellent. We have what we call the ENS operator, and it's one of our pillars of our transformation. And today, it's a Orano toolbox. We can provide services if it's required, because, for example, EDF was interesting with this kind of application because it's bright new tools. And but up to now, it's only, I will say, the guys of Orano can perform the service with these tools.
Excellent. Thank you very much. We are arrived at the end of our session. This was not the unique appointment. That was the first workshop. You can be sure that in the next work program of Euratom in 23-24, you will most probably see some topics, research innovation topics on this fascinating subject. For all the colleagues that participated, some of them since this morning, we had a lot of discussion, presentation of the different topics. Do not hesitate to look at the Euratom work program 21-22 with the deadline on the 7th of October. With such a short time, I'm sure that you will have busy holiday. Dear colleagues, so many thanks to all of you, and I'm hoping to see you very soon in different opportunity and probably also in more presential phase. Many thanks and all the best. Bye-bye.
Okay, thanks a lot.
Bye-bye.